All right, so you have you have the kinetic energy formula, and then you have a field. Okay, this field can also go horizontally. So if the apple's dropping from the tree, magnetism can work from magnetism can work horizontally to your horizontal eyesight, and because gravity is still working from the tree branch to the earth. So I mean, it can work. Um, I should say unilaterally, like with magnetism in the middle and the force or electricity on the outside, to build your field. But then you just have the problem of transformers or transformation, and that's like that could be kinetic energy when you're working with the parabolas, because kinetic energy equals one half mass. Kinetic energy equals one half mass times your velocity squared. Okay. Kinetic energy equals one half mass times your velocity squared. So if you're working with a mass, you're working with a field. It's possible that you're working with a field and not just an object. So a field technically would be a concept, and you'd have to evaluate. You have to evaluate what variables in the field you're working with. I don't know if this is only complicated with kinetic energy, since kinetic energy would have to be like the substance of the field. So that's what's troubling. But so you have a smaller mass, 8, and you have a bigger mass that's 16. Okay, 16 pounds, 8 pounds. And the smaller mass is moving at a higher velocity. This is in accordance with kinetic energy, the theory of kinetic energy. And so the smaller mass is going 10, and the bigger mass is going 5. So it's twice as big, going half the speed, and it's half the size, going twice the speed. And when you look at it in a parabola, this obviously, like these look the same. But if this was a real graph, and this is your smaller, and this is your smaller energy, your smaller energy is I don't really know how. I mean, if the graph was a straight line, because in terms of if you put these two parabolas, um, see like these two measurements, these two measurements of the kinetic energy, the smaller one and the bigger one. It's like you're going to have to put these on a parabola. You're going to have to put these on infinite curve, and it's like that's how. So I just don't understand where the capacity to transfer the energy be, to transfer the energy would be. You'd imagine that the energy would always transfer. I mean, in my understanding, kinetic energy, the bigger mass is always supposed to transfer more energy to the smaller mass. So, and it's supposed to lose mass. It's just if you're putting this on a parabola, then that's going to be your calculation. Because you could fit these two measurements into a curve, into an infinite curve, I'm sure, and come up with a calculation to be able to figure out what energy is going to be stronger. Is the magnetism going to be stronger, or is the electricity going to be stronger? And so you'd imagine that you'd imagine the bigger curve, and it go into your parabola, and then when it gets into the smaller curve, um, like this is when so the bigger curve is going to transfer energy really fast, and the bigger mass is going to transfer energy really fast, and then it's going to hit its transformation peak, its like threshold for transformation, and then that's when it's going to give energy to the smaller mass. Okay, because the smaller mass is going 100 now after the transfer, and well, in totality, the smaller mass is going 100, and then the bigger mass is now going 25. So when it's transferring, um, so so if you look at it on a if you look at it parabolically, technically, when the bigger mass is transferring the energy, like in Newton's cradle, when the bigger mass is transferring energy, technically there's already supposed to be energy that is transforming before it's even impacted, before it's even collided with the smaller mass. So I don't know if that's if that could be like inertia, but because I mean you're talking about this field, you're talking about like working with a field like this. So I mean the apple's gonna fall from the tree uh, at a constant speed depending on the temperature and depending on free energy. Depending on free energy, the apple will fall from the tree at a constant speed every time, and then you're just trying to figure out what this field is, because what this magnetic field is. Because in direct proportion, if this field was vertical, you know, you're not really working with the gravity. You're not really working with the gravity in that way because the apple's not falling. It's not, I would just say the apple is falling from the tree to the ground in a special relative state, but in general relativity would have you say, well, the apple's falling from the tree because there's the magnetic field is the magnetic field is in between the apple, or the magnetic field is working like all over the place. So, but again, like if you're looking at like an x and y axis on parabolic in like a parabolic example, uh, the bigger force is just the bigger force is just doing this, like it's just doing that transformation. But then when the transformation actually happens, okay, it could maybe work like this: like when the bigger mass is transforming energy already to the smaller mass. So when they actually do their full transformation, that's why the smaller mass already has a high velocity, and the smaller mass already has a high velocity, and it just stays. It stays basically. It stays basically. What am I trying to say? Stable in its high velocity now, because it was all. I mean, it was already going faster. It was already going faster, right? It was already going 10, and the bigger mass was going 5, and so it's going 5, and it's already transforming energy, and then by the time it fully transforms, it doesn't. The smaller mass, it's already at its highest velocity. So you have to say that when the transformation actually happens, that it's a very stable higher velocity. If they were going 10, if they were going 10 and 5, and then they went 10, and then they went 100 and then they transformed to 125, you could say that there was a lot of energy. And if that energy had to come from the field, then the field would have to be a general relative field um, that was doing the transformations, because they haven't even like if they're electrons and neutrons or something, they haven't even collided. And how else are you really going to look at the universe? So it's a little bit confusing, but because if you have a field of energy between the bigger mass, if you have like a high energy field, and you have the bigger mass and the smaller mass, then that energy, I would say, in empty space where there's just an endless amount of free energy, then yeah, that gravity is going to work. That gravity can work. That gravity can transform the energy much quicker. But if it's just an apple, if it's just an apple falling off a tree branch, then the energy isn't going to make that transfer. And again, this is like using. I mean, this could be like using the ropes, and because I don't understand the rope hypothesis, but if you can imagine that you have your bigger mass or your Earth, and you have, um, did I even say that right? Well, I don't think I did say that right, but I'm just saying this mag. I mean, obviously, there's going to have to be a line. It's going to have to be like a line of inertia that gravity is already transformed for the particles to be able to even utilize gravity. So yeah, the bigger mass and the smaller mass, they have to use a line, um, or I would agree a rope of gravitational pull, or a rope of gravity, because they're always. I mean, if you think about the magnetic field, there's always going to have to be it's going to have to either be the force, something's going to have to be transforming the magnetism. So it's going to have to be force or electricity, I would say. Um, there has to be like some conduction and all that, something like that. I mean, um, it's gonna have to either conduct or repel um, the electricity somehow. In terms of like your unified field. Um, so I'm just saying, yeah, like the apple could fall off the branch and have a systolic uh, line of inertia that is working in the magnetism, like whether it is like two vectors, um, like a vector going to the ground and a vector going to the apple, or a vector going to the big mass and a vector going to the small mass, and they work in proportion with each other, um, from a zero point. And there has to be, I mean, because there has to be some type of field to be able to. There has to be some type of field to be able to transcribe the parabolic utility like of this equation. So yeah, that's about all I got. And yeah, so I was just talking about like put the kinetic energy, do the math, and work with two you have to work with two material objects in a field, and then if you put it on a parabola, if you put it on the parabola, you'd understand that the bigger mass has to transform the energy to the smaller mass, and you'd understand that it's transforming energy already before it gets to the smaller mass. So by the time it gets to the smaller mass, that the energy theoretically has already been transformed, so it's going to go at a stable velocity, a very high stable velocity, and and then you have a field. I mean, I really like working with magnetism and fields and force and electricity. It's just that to be able to like turn this into like Newton's rings, or have something where there is a systolic where there is a systolic pattern in the universe. And I mean, because if you're talking about Newton's rings, well, why don't you just put um, the hyperboloid inside another hyperboloid, inside another hyperboloid, inside another hyperboloid, inside another hyperboloid, and that is like your field of force. Um, Instead of having Newton's rings, Newton's rings equation is a really easy equation to understand, and you just understand because you just understand how like one little point of energy can transform its energy through just circular energy. Like, the equation is really easy to look at, especially when uh, Noether does it, because Noether does I think they're called Noetherian rings. And when she does it, the equation is just so easy to look at, and you just understand how your point of energy, your point of energy, or because you're not gonna be able to call. Even if you call it empty space, it still has chemical components, right? If you call, you can't call something empty space because it'll have a chemical component. It'll have a temperature component. It has to have hydrogen in it, I would say. So, correct me if I'm wrong. So when you're working with a 0 point and you have that systolic atomic bond, and then that bond is just growing, if that bond is growing in unilaterally in direct proportion to the energy that is indirect proportion that the energy is transforming it, then yes, the masses around, or the circles, or the masses or the energy around that 0 point, that hydrogen bond, they have to be bigger. So that's why they're transforming the energy. They're transforming the energy. They're transforming the energy, and then when the transformation happens, there's a stable, there's the stable velocity that the smaller mass, the hydrogen bond, returns with. So that's why it's like a pulse. All right, I think that's definitely enough. Yeah, that's enough.